It is a delight to come your way once again on the Joy Learning Revision Show. Anekwabi Albert is my name as usual. You can call me Pause. And I'm going to take you through revision in physics. Exams are fast approaching, and I'm happy to be here to help you catch up with the things you really need to recap before you get into your exams room. So we are streaming live on Facebook, Joy Learning Television. We are also on YouTube, Joy Learning Television. So get others on board as we go through the things that we need to remind ourselves of as we prepare for the forthcoming exams. If you've been following us on this channel for some time now, I have gone through some areas in the part 2 of the physics paper. I'm talking about the theory paper, part 2. I've gone through question number 8 on mechanics. I've gone through question number 9 on heat, energy, work, and power. I've gone through question number 10 also on light and wave phenomenon. And today I'm going to take you through question number 11, electric and magnetic fields. So if you think that that topic is quite dicey or difficult, I'm going to break it down to your level for you to understand what you need to get firm grips on as you go to write your exams. So call your friends, tell others to join in as we revise and as we study. Now, I would need you to also do me a favor. Get your pens ready, get your books ready to solve the problem of the day. Okay, so as we go through the revision show, you would have the opportunity to solve the problem of the day, and then you can call in. You can call in and give your answers. And I bet you I'll give you another number to call for your prize if you are able to get the questions or the answers correctly. So to start with, let us look at the problem of the day. We've displayed them on our social media pages, and I'm going to just remind you of them. Question number 1A for problem of the day says distinguish between electromotive force of a cell and potential difference across it. Distinguish between electromotive force of a cell and potential difference across it. In fact, if you follow what I'm going to do this evening, by the time I'm through, you would be able to give this distinction without any difficulty. Then 1B says, state 2 effects of an electric current. We will look at that one too. State 2 effects of an electric current. Then CI says, a battery of EMF 12 volts and internal resistance 1.5 ohm is required to give a current of 0.5 ampere when connected to an external load of resistance R. What is the value of R? That's quite basic. And we'll go through this area too, so you could be able to answer this question. Then it goes on to say, the resistivity of a wire is 6.25 times 10 to the power minus 7 ohm meter. If the resistance and cross-sectional area are 7 ohms and 0.55 meters squared respectively, calculate the length of the wire. That's a question on resistivity, and you have to try and work it out. Then it says, what are magnetic keepers? So if time permits, we'll also look at something little on magnetic fields. And to start with, we'll look at what are magnetic keepers. And it says a coil having 1,000 turns and a length of 31.4 centimeters carries a current of 5 amperes. Calculate the, it says, magnetomotive force, MMF. Magnetomotive force, and then magnetizing force. Magnetizing force. That is our problem of the day. And I expect you to try your hands on it. And then as we move on, I'll give you the opportunity to call in and also give your solution. All right. So tonight, I'm saying we're going to look at electric and magnetic fields. And for the start, I know we're going to get an opportunity to look at this again some other time. So I'm going to look at direct current circuit analysis. Direct current circuit analysis. Now, when we talk about direct current, you're looking at current that moves or that flows in only one direction. In only one direction. Unidirectional current. That's it. So, to start with, we want to look at what is electricity. And I'm saying electricity is a form of energy that consists of electric charges. It is a form of energy. Well, that's okay. And it consists of electric charges. So when I talk about electric charges here, basically I'm talking about electrons. So we are saying that this form of energy is made of electrons. That is it. Electrons. And so when you have these electric charges, which I'm calling electrons, flowing, then current will be produced. So in other words, when electrons flow or they move from one point to the other, current is produced as a result of the movement of these electrons. All right. So that's it to build our foundation. We move ahead. So, one look at what we call the electric cell. Electric cell. And I'm saying that it is a device that produces, it gives us direct current. So you can't define an electric cell without bringing direct current. You shouldn't just say it produces or it gives us current. No, because you could have alternating current and we also have direct current. So for an electric cell, it's going to give you direct current through chemical reactions. So when you pick an electric cell, it has got chemicals in there. In fact, when you pick an electric cell, you'd expect to see electrodes. Positive electrode, negative electrode. So a positive side and negative side. And these electrodes are inserted into a chemical, which we could call the electrolyte. So this electrolyte could be in the form of a paste, powder, a gel, or liquid. So reactions that take place between the chemicals and the electrodes will help the cell to give us a direct current. So it is a device that produces direct current through chemical reactions. All right. So when you have a number of cells put together, you get what we call a battery. So to my left, let me give you the circuit symbol for a cell. So in a circuit, you could just have this and that. And you have this. These are just wires. So this is positive electrode, negative electrode. That is the circuit symbol for a cell. And I'm saying that a group of cells, a number of cells, two or more cells put together gives us a battery. So I'm going to have something like this. All right. So I have the positive electrode, negative, positive electrode, negative. So with that, I have a number of cells put together, and that's giving me a battery. A battery. That's quite easy to recollect. So you have two or more cells put together, it gives you a battery. So the one that you call a battery, usually we mistakenly take just one cell and we say it's a battery. No, but when you pick one cell and you pick another one, together you put in the cell holder, and then that becomes a battery that you're going to use. All right, so we quickly move on. Now, I want to look at what is the relationship between quantity of charge, current, and time. We have established that current will only be produced when charges move, and that's when electrons flow or they move. And as they move in a time t. So we are saying that when a circuit is closed, so in this case, as we revise, let's look at what we call a closed circuit. When we say a circuit is closed, what do we mean? We mean that the key is on, the key has been closed, so current will go through the circuit. In that case, we say it is a closed circuit. So a closed circuit is one in which current flows. If the circuit is opened, it means current will not flow through that circuit. So when a circuit is closed or completed, okay, quantity of charges flow. And here, the symbol for quantity of charge is Q from the cell. And as the charge flow or charges flow, current I will be produced as a result for a time t. So these three quantities, Q, I, and T, how are they related? Then I'm saying that these three are related by quantity of charge is equal to current times time. A very basic but important relationship that you have to keep. Q is equal to I, so Q is equal to current I times T. Simply Q is equal to I T. That's quantity of charge is equal to current times time. We have established that. Let's move ahead. If I would want to make my current the subject, so I have Q is equal to IT. I will give me Q on T. Now, the unit for quantity of charge is coulomb, and that for time is second. So that gives us coulomb per second. Good. So it means that the unit of current, which is ampere, so unit of current, ampere, A. This implies that the ampere consists of coulomb per second. Coulomb per second. You could meet some of these in the objective test. So we can go ahead and try our hands on an example. Let's look at an example. Let's see how we go about it. We have the formula Q is equal to IT, and that should help us solve the question. All right. It says, find the current that flows if 8 coulombs of charge pass through a wire at a steady rate in 0.033 minutes. After this question, I'll give you the chance to call in and solve the next question. So as I do, you watch. Then you try your hands on the next question. Okay. So we are asked to find the current that flows if 8 coulombs of charge pass through a wire at a steady rate in 0.033 minutes. So let's look at our solution. All right, let's put our data. We'll be given quantity of charge Q to be 8 coulombs. That's okay. We have been given the time T to be 0.033 minutes, but the SI unit for time should not be minutes, it should be second. So we change the minutes to second. How do we do that? You're going to have 0.033 times 60, and that gives us 1.98 seconds. I hope you are following me. So what do you want? You want current. So current, our symbol says I. From the formula Q is equal to IT, I will be equal to Q on T. So our I is equal to Q on T. I is equal to Q on T. We have our parameters already. So we're going to get Q to be 8. T is 1.98. We divide 8 by 1.98. And that should give us 4.04 ampere. Don't forget, it's current. So the unit for current is ampere. So 4.04 ampere. And that is it. Good. Now, tonight our phone lines are 030-2211-705, 030-2211-705, or 030-2211-706, 030-2211-706. I am sure you have the phone lines on your screen pretty shortly. So, with this understanding, let us look at this example. And I would want you to try hands on this one. A wire carries a current of 100 milliampere. So pay attention to the unit attached to the value given to us. 100 milliampere. Calculate the time taken by 5.0 times 10 to the power 20 electrons to pass a given cross-section of the wire. Then it says magnitude of electronic charge is equal to 1.6 times 10 to the power minus 19 coulombs. This is a past question. 2019 WASSCE Physics Practical for Alternative B. Usually you'll be given a practical question for 21 marks plus precautions. Then the part B will ask you simple short questions for 4 marks on the practical. And this question came there. How do you approach this? I've given you the formula, I've laid the foundation, I've solved a question. You can call in and we try and solve this question together. So I'll be expecting your call via 030-2211-705 or 030-2211-706. Look at the question on your screen. The wire carries a current of 100 milliampere. You can be putting down your data because I'll move on as I take you through the revision and you try your hands on this one. And if I ask to calculate the time taken by 5.0 times 10 to the power 20 electrons to pass a given cross section of the wire, then you have been given the magnitude of electronic charge to be 1.6 times 10 to the power minus 19 coulombs. I am sure that you will be able to do something about this question. So you have some few minutes, try your hands, give me a call, and let me hear what you have for us so we can move on. Types of cells. We're looking at an electric cell. We have basically 2 types of electric cells that are supposed to be discussed at your level. 1, primary cells, and 2, secondary cells. Primary cells and secondary cells. So quickly, we look at what is a primary cell. What is a primary cell? I'm saying these are cells that produce, once again, you can see direct here. They are cells that produce direct current now by an irreversible chemical change. They produce direct current, good, by a chemical reaction, good. But this chemical reaction is irreversible. Once it takes place, it continues to take place with time. It cannot be reversed. And because that chemical reaction cannot be reversed, they cannot be recharged after use. You can't use the cell, and when it runs down, you recharge to use. No, you don't have that laxity because it is a primary cell. So it produces current for us, that is current, through an irreversible chemical change And because of that, they cannot, or it cannot be recharged after use. And that is a primary cell. Now we move on. Examples of primary cells, we have the simple primary cell. The simple primary cell. Otherwise called the simple voltaic cell. That's an example of a primary cell. And this is the diagram giving us a simple primary cell or a simple voltaic cell. And this cell is being used to light up a bulb. Okay, so you can see light somewhere there. Now, I told you that when you pick a cell, you look at what we call the electrodes. So these are the electrodes. You can see zinc electrode. You can see copper electrode. So you have positive electrode and you have negative electrode. Then the electrodes are immersed into this solution, dilute sulfuric acid, and this becomes what we call the electrolyte. In this case, it is in the form of a liquid. It could be a gel, it could be a paste, it could be a powder, all that. So this is a diagram of just the simple primary cell. Now, there are two things that I would want you to try and find out about this primary cell. The defects of this primary cell. The first one I want you to look at is polarization. Polarization. One of the defects of this primary cell is polarization. So, what is polarization? Then, you can also see that in this diagram, there are what we call hydrogen bubbles. See them? Trying to settle around the copper electrode. And they will end up insulating portions of the copper electrode. In that case, they will end up reducing the surface area of the copper electrode that will be in contact with the solution for the reaction to take place. All right, so I have a caller on the line. Hello and welcome. Good evening. Hello?
Hello.
Yeah, you're welcome. Good evening.
Bye.
What is your name, please?
My name is Mabel.
Mabel.
Yeah.
Mabel, are
Yeah.
you here to help us answer the question?
Yeah.
Okay, so Mabel, I'm listening to you. Where are you calling from, please?
Is that
Where are you calling from, please?
Central Region?
Which place exactly?
Is that
Where exactly in the central region are you calling from?
I'm not able.
Agona Swedru. Good.
Yeah.
So go ahead, please. What do you have to say about the question?
Question.
Yes. Do you have a question for us? You want to say something about the show? Yeah, so we are listening. What do you have for us? All right, it looks like you are lost. We have a question for you to try and answer. So if you have an answer, you can help us with it. All right, I think Mabel is a little bit lost. I have a question that I gave out earlier on, and I would want you to try and then help us answer the question. So it says that a wire carries a current of 100 milliampere. Calculate the time taken by 5.0 times 10 to the power 20 electrons to pass a given cross-section of the wire. Then we'll be given the value for electronic charge to be 1.6 times 10 to the power minus 90 coulombs. That is the question that we are trying to answer. So if you call in, you try and help us answer the question. Or if you have any questions about what I'm taking you through so far, you can ask that question. So we will quickly move on to what we're looking at. So we're looking at the simple primary cell. The simple primary cell. And I'm saying that there are two defects of the simple primary cell. The first one is what we call polarization. Polarization. And the second one, I was trying to show you that you can see one defect being shown here. You have hydrogen bubbles being produced. They were not originally part of the cell, but due to reaction taking place between the electrodes and the electrolyte, we find them being produced. And then they move to the copper electrode and try to settle on its surface. And by so doing, they end up insulating portions of the copper electrode, reducing its surface area that is involved or that will be involved in the reaction. Now, the second defect is called local action. Local action. So these two defects of the cell are very important that you get to know what they are and why they come about and their effect on the simple primary cell. So polarization, local action, they are two main defects of the simple primary cell or the voltaic cell. And it will help you to try and read a little about that. Now we move on to other examples of primary cells. We have the Daniell cell. So we looked at the simple primary cell or the voltaic cell. The next example is the Daniell cell. The Daniell cell. Then we also have the Leclanché dry and wet cells. The Leclanché dry and wet cells. These are but a few examples of simple primary cells. We can move ahead and look at secondary cells. We said that for the primary cells, they produce direct current through an irreversible chemical change. Therefore, they are not rechargeable. They cannot be recharged. Look at secondary cells. For these ones, they produce direct current also, fine, by a reversible chemical change. They produce direct current by a reversible chemical change. So I could have the chemical in them reacting, and then the chemical energy will be converted into electrical energy. Then when the reaction has taken place for a long time and they run down, we can recharge. So now we plug in and now store. We convert electrical energy now, store it, and then later it will be used by the user of the cell. So we are saying that because they have a chemical reaction or a chemical change that is reversible, they are known as accumulators, storage cells. In one way, they are giving out current. They are discharging. In other way, they are storing. So they can discharge and then they can store for use also. Therefore, they are rechargeable. They can be recharged. We can recharge them when they run down. So when you pick any cell and it can be recharged when it runs down, then that cell is very likely to be a secondary cell. A secondary cell. A secondary cell. All right. We can go ahead and look at some examples of secondary cells. So examples of secondary cells would be the lead acid battery, mostly used in cars, so like the car battery, the lead acid battery. Then we have the alkaline accumulator. That is also an example of a secondary cell. That's an example of a secondary cell. All right, so before I move on to electromotive force, that will help us to solve the problem of the day. I'll just take a little break, a breather. When I come back, we will solve the question I gave earlier on about the quantity of charge equal to current times time. Then we'll go ahead and look at electromotive force. So stay glued to your set. I'll be back in just a jiffy. So on your screen, you will have the question I gave earlier on. And I'll help you to try to get the solution. Let's start by putting down our parameters. From here, we have the current being 100 milliampere. So I'm going to use I for current. So I is equal to 100 milliampere. We change to the SI unit for current is ampere. Hello.
Hello, sir.
Good evening.
Good evening, sir.
May I know your name, please?
My name is Joseph.
Okay, Joseph, where are you calling from, please?
I'm calling from Agron Quanta.
Agron Quanta. All right. So please go ahead. What do you want us to
Okay.
discuss?
So in the question, our parameters, they give us the I, which is the current, to be 100 milliampere.
Okay.
So for that one, we get the milli is times 10 to the power negative 3.
Okay.
So we have 100 times 10 to the power negative 3, which will give you 0.1.
0.1 ampere. That's good.
So and we have a formula which is saying that the charge is equal to the current times the time.
All right.
And also we have the number of electrons. Multiplied by we have the number of electrons multiplied by the E, which is 1.6 times 10 raised to the power negative 19 coulombs. So we have when we equate it, we have E, which is what we are going to find to be N, capital N-E over I. So we have our T to be equal to 1.6 times 10 raised to the power negative 19 times 5 times 10 raised to the power 20 all divided by 100 times 10 raised to the power negative 3, which is the 0.1. So when we simplify it, we get 800 seconds. Yeah, so that is the time taken.
Joseph, that is brilliant, excellent. In fact, I applaud you. Are you a final year student?
No, please, second year.
Wow, that's impressive. Where do you school?
Takwa Senior High.
Wow, Tasku.
Yeah,
you're really doing well. I'm proud of you. You've done well. Thank you for calling in and keep watching.
You're welcome.
All right. Wow, so that is it. That is exactly all that I was expecting from you. Joseph has called from Agona Nkwanta, a student of Tasco, second year student, and he has done justice to the question. So I put down all that he was saying as the solution. He changed the current from the milliampere to ampere by multiplying the value by 10 to the power minus 3, giving us 0.1 ampere. He gave us the formula he was going to use. Q is equal to current times time. That's okay. And he's saying that to find the total charge, you need to multiply the number of electrons by the charge of an electron. So he said Q should be equal to NE. So if Q equals NE, then you have NE is equal to IT. So making T the subject, you're going to get NE over I. Very good. Excellent. So he put in the values just like that. And we have 800 seconds. So that is what I was expecting from you. And I thank Joseph so much for doing that. That is very, very impressive. So we can go ahead and quickly look at what I was going to talk about. Electromotive force. Electromotive force, also known as EMF. EMF. Electromotive force. Usually, I would just say, for the start, for you to just get to understand it, you would say EMF is the driving force. I'll get to the technicalities. The driving force that helps push currents out of a cell. So the question is, I have a cell or a number of cells, a battery. Maybe I have a torchlight. I put them in a torchlight. I put the torchlight on. and then I have light. How? How does that happen? What is inside the cell or the battery that helps the current to flow, to help the bulb of the torchlight come on? So I'm saying that just to build a foundation, let us consider EMF as a driving force. And this driving force is helping us to push current out of the cell. But this is not a definition that you can write in exams and get a mark. No, it is just to give you an idea about what we're talking about. So as we go ahead, we will look at more acceptable definitions. So, talking about EMF still, let's take an example. A cell of EMF E. So that's our EMF. And it supplies electrical energy W as current I flows from that cell within a time T. So, how are these quantities related? We are saying that the electrical energy supplied by the cell, which is W, is equal to the current that flows times the EMF times the time. So, W will be equal to IET. W equal to IET. All right. If you make E the subject, since we are looking for EMF, E becomes W over IT. W over IT. All right. So let's move ahead. Now we have this formula to take note of. E, which is our EMF, is equal to W, which is our electrical energy supplied, over the current times time. That should remind you of something. So E is equal to W over IT. If I have that, so E is equal to W over IT. We just found out that Q is equal to IT. Therefore, in place of IT up here, I can put Q there. So I could say, yes, E is equal to W on Q. E is our EMF. W is our electrical energy. So E is EMF. This is electrical energy. And Q is charge. With this, we can get a definition for electromotive force. Electromotive force. E is equal to W on Q. So will you try that? Will you try that on your own? E giving us W on Q. So with that, we can write our own definition for electromotive force. So try it and let's see the definition. I will later on ask you to call in and get the difference between this one and potential difference. All right. So we move on. What is the unit of EMF? It's volt. So each time you measure EMF, you attach the unit volt to it. Volt to it. We move on. Potential difference. Now, potential difference, which is PD, between any 2 points in a circuit, one is the work done when one coulomb of charge moves from one point to the other. The potential difference between any 2 points in a circuit is the work done when one coulomb of charge moves from one point to the other. So work is done as the charges move from one point to the other. So probably there's a load, okay? And we need current to make the load work. So charges will flow through and then current will be produced and the work will be done. So the work done when it's a coulomb of a charge moves from one point to the other in the circuit is what we call the potential difference across the circuit. Good. So now that we have seen EMF giving us E is equal to W on Q, electrical energy supplied on the charge. And now I've given you PD as the work done when one coulomb of charge moves from one point to the other. What then is the difference between the EMF of a cell and the potential difference across the cell? What is the difference between the EMF of a cell and the PD across the cell? Very soon, you get the opportunity to call in and give me your answer. Let's move on. Now, the SI unit of potential difference is volts, just like the SI unit of electromotive force, which is EMF, is also volt. So both have the same unit, which is volt. Now, the instrument used to measure potential difference is the voltmeter. In the same way, if you want to find the EMF of a cell, you still need the voltmeter to do that. All right. Now, I will pretty shortly show you how you can do that. But what is the circuit symbol of a voltmeter? Okay, I have a caller on the line. Hello and good evening.
Hello, please good evening.
May I know who is speaking, please?
Please, I'm Kendra, a first year student.
Kendra,
a first year student.
Okay, where are you calling from?
I'm calling from New Legon, Accra.
Okay, Kendra, what do you have to tell us?
I want to give the difference of the electromotive force and the potential difference.
Super. Go ahead, please.
Okay, so the electromotive force will be the driving of electric force from a cell or generator.
Okay.
And then the potential difference will result from the current passing through a resistance within a circuit. And so therefore the electromotive force is the cause and the potential difference is the effect.
Okay. That's pretty interesting. All right, Kendra. I appreciate your call and your contribution, all right?
Okay.
Thank you for watching. Keep watching, okay? You've done really well.
Thank you.
Thank you too. Good. So Kendra has brought us, she has shed more light on EMF and potential difference. That's good. And I like her understanding of the cause and the effect. That's pretty good. Thank you. And she's a first year student. So that's a promising physics student. I'm proud of you. That's good. So we're looking at the symbol, circuit symbol for a voltmeter. So you have that, you have V in it, then it goes, and it goes. So that becomes circuit symbol for a voltmeter. If I want to make it quite boldly, all right, and that's that. I have that. That's a voltmeter. So if you see this in a circuit, it's simply a circuit symbol for a voltmeter. All right, we move on. So I'm looking at measuring EMF of a cell. If you are going to write the physics WASSCE exams, pay particular attention to this. Very often in the practical work for electricity, you will be asked to measure the EMF of the cell. Or you'll be given some batteries. You're going to use those batteries in the experiment. And the question might say, find or measure the EMF of the cell. Now, what do you do? Let's say I just have a cell. So this is the negative side and this is the positive side. And I have another cell. So now I've joined them in series. Okay. I still have positive side and the negative side. So negative, positive, like this. So that's my cells or my battery I'm going to use for the experiment. If you want to find the EMF, what do? Simply connect this side to the voltmeter straight away. And then this side also, the voltmeter. Any reading you get on the voltmeter becomes the EMF of the cell. Very simple. And you do this before you even connect the circuit. So whenever you want to find the EMF of the batteries or of the cells, you connect them directly to the voltmeter. Now, let me say this. Even if the question does not ask you to find the EMF of the cells, please do it. Find the EMF first before you start the experiment. Why? The EMF will tell you whether your batteries are weak, whether they are dying out or not. If you pick a cell, usually you have 1.5 V written on it as its EMF. If you are using 2 in a cell holder, then you are supposed to get about 3 volts. So if you find an EMF and it is less than 2.5 volts, it tells you that that cell or that battery really is about dying. It's getting used up. So then what do? You try to change. So even if you are not asked to find the EMF, it is advisable to find it and check whether your batteries are strong enough or not before you even start the experiment. So please, to find the EMF, you don't even need to start the connection. You only have to take your batteries, put them in the battery or cell holder, connect them directly to the voltmeter, and then you read from the voltmeter. And whatever value you get becomes the EMF of the cell. And if it is less than 2.5 volts, I will recommend that you try to change the cells. Okay, so we go ahead. So we are saying distinguish between electromotive force of a cell and potential difference across it. I've given you a formula for EMF, E giving us W on Q. I've told you that PD is the work done when one coulomb of a charge moves from one point to the other in a circuit. So what then will be the difference between EMF and potential difference across a cell? If you have another view, if you have a submission, you can call in and then you do that. 03022111705, 03022111706. So you can call in and then we discuss that. Okay, Joseph.
Okay, sir.
Are you the same one who called earlier on?
Yes, please.
Welcome back. What do you have to tell us this time?
Okay, so the potential difference is a scalar quantity.
Okay.
And the EMF is a vector quantity.
Oh, okay. Are you saying so because of force attached to like electromotive, like force?
Yeah, electromotive force.
Okay. I get where I come from.
It's a vector quantity.
Okay.
Yeah, so the electromotive force is a vector quantity and the potential difference is a scalar quantity.
Oh, okay.
And also the potential difference is the work done, is the ratio of work done to the charge.
Okay.
Whereas the electromotive force is the ratio of the energy, the electrical energy to that of the charge.
Okay.
Yeah.
Okay, Joseph.
And also I have the potential difference. The potential difference, when we define it, is the work done per unit positive charge in moving the charge from one point of lower potential to a point of higher potential through a load.
Okay.
And the force needed to drive the positive charge from a point of lower potential to a higher potential is the electromotive force.
Yes, so I am happy with your later submission.
Thank you.
That one I think is very good and you need to be available for that.
Thank you very much.
Thank you, Joseph, for calling in. Yeah, thank you so much. I appreciate the call. let me throw a little more light on Joseph's submission, the earlier ones. Talking about the EMF being a vector quantity and then PD being a scalar quantity, you can't really tell the direction of EMF. Although the name is electromotive force, the force is quite deceiving, okay? So both EMF and PD, we can't tell the direction in which they are moving, no. Well, you can't really trace them though. So don't really talk about they being scalar or vector quantities. Just let them go and look at the definitions. Okay, hello, good evening.
Good evening, sir.
May I know your name, please, and where you're calling from?
Yes, my name is Joylearning Daniel.
Come again.
My name is Joylearning Daniel.
Okay.
Calling from Bono East Region.
From Bono East Region. Good. Daniel, you're welcome to the revision show. What do you have for us?
Thank you, sir. Please, I want to differentiate between electromotive force and potential difference.
Good, my brother. Go ahead.
Okay. With the electromotive force,
okay,
is the amount of energy.
Okay.
Is the amount of energy given to each column of a charge.
Okay.
The potential difference.
Okay.
Is the amount of energy utilized by one column of charge.
Okay. Okay. All right, Daniel. That's a good one. I appreciate your calling in. Thank you, and keep watching, okay?
Okay.
All right. So our callers have done well. They've tried to give us the way they understand EMF and then potential difference. And I would like us to look at my suggested solution. We are looking at the definitions of EMF and potential difference. Those definitions will help us to really get the difference. So we could say that the electromotive force is the electrical energy supplied per unit positive charge. Electrical energy supplied per unit positive charge. Why? We wrote the formula that E is equal to W on Q. And W is the electrical energy supplied. And Q is the quantity of charge. So we can define electromotive force as the electrical energy supplied per unit positive charge. So if just a unit positive charge, okay, decides to move through the circuit, what will be the energy that it will supply? That's EMF. Then we are saying that PD, or potential difference, is the work done. It's the work done. Do I have a caller on the line? Hello, Salamatu, good evening.
Evening, sir.
Please, where are you calling from?
Please, I'm calling from Ketimine.
Okay, please go ahead with your submission.
Please, I want to differentiate between the potential difference and the electromotive force.
Yes, please, go ahead.
The potential difference is the work done per unit positive charge in moving the charge from a point of lower potential to a point of higher potential through a load.
Great, that's good.
While the electromotive force is basically used to set up voltage across any load in the circuit so that the current can flow through them.
Excellent. Excellent, Salamatu. Thank you. Thank you. Well done. Well done for calling in. So she's done just what I expected us to go through or to do. So that's it. So that's, as I was saying, from the formula E equals W on Q, we can say electrical energy supplied per unit positive charge is the EMF. Then the PD, or potential difference, is the work done in moving a unit positive charge. Well, mostly they'll say from this potential, the other potential. But if you just say moving a unit positive charge round the external circuit, you'll be given a mark. So the work done in moving a unit positive charge round the external circuit, and that gives us the potential difference. I am really impressed at the way you have been able to call in to make your submissions, and I think you are doing really, really, really well. Keep it up. Keep it up. So we are building and are going higher and higher. Good. Now, with the problem of the day, the next question is state two effects of an electric current. The phone lines are still activated. You can call in 030-2211-705 or 030-2211-706. What are the effects of an electric current? In other words, when current goes through, let's say, a conductor, okay, what will be the effect of the current on the conductor? That is all we are asking you to tell. So, state 2 effects of an electric current. You can call and give me your answer. I'll be very happy to hear from your end. So, I'll go on with the revision, and then when you get your answer, you call in, and then we talk about it. Good. Now look at electrical resistance. When we say electrical resistance, R, what do we mean? Resistance is opposition. Opposition to the flow of electric current through a circuit. The opposition. So this tells you that as current goes through a circuit, there is an opposition. There is something that tries to prevent the current from flowing through the circuit. And the current will have to overcome this opposition. So it could move from one point to the other. And that is what we call electrical resistance. So it is the opposition to the flow of electric current through a circuit. All right, I have Augustine on the line. Good evening, Augustine. Oh, I think I've lost Augustine. Please try again, okay? Come again. I would like to hear from you, Augustine. Okay, so opposition to the flow of electric current through a circuit is what we call electrical resistance. Now, the measuring device is the ohm meter. You have to please take note of this. Very often, because it is resistance, students think that the measuring device is a resistor. No, a resistor is a resistive body, a body introduced into a circuit to resist, to oppose the flow of current in a circuit. So a resistor is not a measuring device. It cannot measure resistance. But the one that, or the device that will measure resistance is the ohm meter. Very important, so take note of it. Now, resistance is a scalar quantity. Why? We can tell that there is opposition to the flow of current, but we cannot tell whether the opposition is done to the left, the right, or where. You can't tell the direction in which the current is being opposed. Okay? So it has a value, no direction. So resistance is a scalar quantity. Its measuring device is the ohm meter, and the unit of resistance is the ohm. It's the ohm. So resistance, opposition to the flow of electric current in a circuit. It is a scalar quantity. Its measuring device is the ohm meter, and the SI unit is the ohm. I am still waiting for your call. We want effects of electric current. When current flows through, let's say, a conductor, what will be the effect of the current on the conductor? If you have an answer, you can call in and then we look at it. Then I want to look at internal resistance. Internal resistance. So we looked at resistance in general, where there is opposition to current flow in a circuit. Now I'm narrowing in to internal resistance. So this one, it is resistance coming from within the cell itself. So the cell itself, that is even amazing. The cell is supposed to give us current, but the electrolyte, the electrodes that make up the cell. All right, Joseph is back. Hello, Joseph. Good evening.
Hello, sir. I have the answer for the effect of electric current.
Okay. Go ahead, I'm listening.
My first answer is magnetic effect.
Magnetic effect.
Yes, please.
Okay, go ahead.
I also have thermal effect or heating effect.
Thermal or heating effect.
Yes, please. And the last one, I have chemical effect.
You have chemical effect.
Yes, please.
So, Joseph, you will be the first person to receive a prize tonight.
Thank you very much.
So, I want you to call this number. A nice, fine lady will answer your call and help you to get your prize.
Thank you very much.
So 055, take the number down. 055.
055.
Good. 86.
86.
33.
32.
No, 33. 33.
33.
Good. 684.
What? Say, come again.
684.
684.
684.
684.
Yeah, let me take it again. 055.
Yes, please.
86.
86.
33.
33.
684.
684.
No, 688. As in 8.
8.
Good. 684.
Okay, sir.
Good. So please call her and she will give you a nice award. Okay, a nice prize.
Thank you very much.
Thank you. So Joseph has given us what I was looking for, all that I was looking for. Effects of an electric current. When current goes through a conductor, 1, it could turn the conductor into a magnet. It has the ability to create magnetic field around the conductor. And with time, it could make it behave like a magnet. So it's got magnetic effect. Then it could change even the chemical properties of that material. So it's got a chemical effect. Then, because of opposition, because of resistance to the flow of the current, there may be some heating effect. Or we call it, you say, thermal effect. Thank you, Joseph. Thank you. Joseph is a senior high school 2 student from Tar School. We have to come and look for you wherever you are. You are really doing well, and we are proud of you. Keep watching Joy Learning Television. Good. So we were looking at internal resistance. So I'm saying that this resistance is not coming from elsewhere or outside. It's coming from within the cell. No wonder if you buy just a new cell and you keep it in your room, you don't use it. It stays there for a long time. You go and it's no more, cannot be used. It can no more be used. It's died off. Why? Internal resistance. So as the cell is there, there is opposition going on within the cell. So it is opposition 1 to the flow of electric current by the chemicals and electrodes within the cell. Within the cell. So within the cell itself, its own constituents are opposing the flow of current through the cell. And that's what we call internal resistance. So even if you don't have an external resistance in the circuit, just the cell itself has got internal resistance. That's quite amazing. So the circuit symbol, usually, you could have a cell like this, then attached to it is this and that. So you can have that there. Or it could be that and that. Then you have this with a small r, like that. So these, any of these could be the circuit symbol for internal resistance. So you can see a cell here. That's the cell. And just close to it is this resistance, telling you that the resistance is coming from within a cell. That's internal resistance. Good. Once it's also resistance, but it's just internal resistance, the unit of measurement will be the ohm. Okay. Now, we want to look at Ohm's law. Ohm's law. Because I would like to do Ohm's law and internal resistance as a recap. Now, what's Ohm's law? Ohm's law says that the current flowing through a conductor, so the current flowing through a conductor, is directly proportional to the potential difference across the conductor. The current flowing through a conductor is directly proportional to the potential difference across the conductor. Now, there's a condition. This provided the temperature and pressure of the conductor remains constant. So you can pick it from the tail end. Provided the temperature and pressure of a conductor remains constant, they move ahead. The electric current flowing through a conductor is directly proportional to the potential difference across the ends of the conductor. So, electric current flowing through a conductor is directly proportional to the potential difference of PD across the conductor if the temperature and the pressure of the conductor remain constant. Good. Now, we can write a mathematical expression for Ohm's law. Don't forget that it says that the current that is going through a conductor is proportional, directly proportional to the PD. So if I equals current, V equals potential difference, or PD, then we say V directly proportional to I. Then we take away the sign of proportionality, we introduce a constant. That becomes V equal to IR. So this time, R is a constant of proportionality, and it is the resistance of the wire. So in short, Ohm's law could just be V equals IR. V equals IR. Current through the conductor is directly proportional to the PD across the ends of the conductor if temperature and pressure remain constant. Now we can work around this and look at some other stuff. We just saw that from Ohm's law, you have V is equal to IR. I would try to get a graph or about two graphs from this expression. So let's look at it. From V equals IR, I would like to plot a graph of V on the vertical axis and then I on the horizontal axis. So a graph of V on the vertical axis against I on the horizontal. Now my issue is, how is this graph going to look like? Well, let me compare the equation I have with that of a straight line. So I'm going to have V equals IR. Then Y is equal to MX plus C. Because I'm going to plot I on the horizontal axis, the X axis, I'll rewrite this as V is equal to maybe RI and then plus, there's nothing there, so I'll put 0 there because I'm going to compare to find out how the graph will look like. Now, what do I see? I can see that if I plot Y or V on the Y axis like this, so I'll draw my Y axis somewhere this way. Then maybe I put V there, PD in volt. Then I want to plot I on the X axis. So I on the horizontal axis. So I have current in ampere here. the intercept should be this, and I'm seeing 0. So it tells me this particular graph is going to begin from the origin, or is going to pass through the origin. Fine, that's good. Let's move on. What will be my graph, or how will it look like? Is it going to be an upward graph or a downward graph, or what happened to it? That comes from the gradient. If I look at the gradient, which is m, it corresponds to r, and r is positive. So I'm going to get the gradient positive. That means that my graph will move vertically upwards, and it should pass through the origin, like that. Now, the slope of this graph, which is the gradient, from the comparison, the slope will be equal to R, which is the resistance of the conductor. So very often you are asked, what is the significance of the slope? If you plot a graph of V against I like this, you say the slope represents the resistance of the conductor. Okay, still from the Ohm's law. What if this time I still have V equals IR? So V equals IR. But now I want to plot a graph of I on the vertical axis against V on horizontal axis. So in that case, I'm going to make I the subject. I'm going to get I is equal to V over R. Because I want to compare with Y is equal to mx plus c, I'm going to rewrite that above expression to look like something like y equals mx plus c. So I'm going to get I is equal to, then I'll have V, okay, or let me make it 1 over R times V I want to show the times. So 1 over R times V plus 0. So if I compare, let me put down my axis. I want to write, put I on the y axis. So vertical axis, this, I'm going to put I in ampere there. Then I'm going to try and put V on the horizontal axis, which is x axis. So I put my V there in volt. Then the question is, what will be my intercept? I can see C 0. So I expect that the graph should pass through the origin. Fine. Now look at the gradient. M corresponds to 1 over R. It is positive. It means I'm going to get a graph that's moving upwards, which will pass through the origin like that. And this time, the slope of the graph will be equal to 1 over R. So the slope of the gradient is the inverse of the resistance of the conductor. You have been able to see the dynamics. When you plot V against I, how it will look like, and I against V, how it will look like. So when it's for us to plot a graph, try and look at the formula that relates to the graph, and look at which one is on the vertical axis, which is on the horizontal axis, make which one the subject, and compare with the equation of the straight line, and see how your graph will look like before you even start plotting. Now, any device that uses electricity, current goes through it. You try to plot the graph of current against voltage, should give you maybe a straight line graph or a curve. Depending on the graph that you obtain, there is a name you could give or you can give to the device. Now, from V is equal to IR, we can make R the subject. So if I have V equals IR, then R will give me V over I. R is in ohm. V is in volts. I is in current. This can help us to define the ohm. So we are saying the ohm is the resistance. Why? R is resistance and it's in ohm. So the ohm is the resistance of a conductor, such that when a PD of 1 volt, you see, current will only move or pass through a conductor if there's a potential difference created across the ends of the conductor. So when a PD of 1 volt, so you see V is on top, is applied across the ends of the conductor, and a current of 1 ampere flows through it. That is how you define the ohm. So the ohm is the resistance of a conductor such that when a PD of 1 volt is applied across its ends, a current of 1 ampere flows through it. And the expression V equals IR, we make R the subject, get it to be V on I, will help you to define the ohm, the resistance of a conductor, such that when a PD of 1 V is applied across its ends, a current of 1 ampere flows through it. Good. Now, ohmic or linear devices. As I said earlier on, these devices, when they are in use, when we measure current through them, we get the PD across them. We plot a graph of current against potential difference or PD against current. It's going to produce a straight line graph. It's going to give us a linear graph. We call these devices ohmic devices or linear devices. These are devices or loads that obey Ohm's law. They obey Ohm's law. They have a linear current voltage relationship. So when we plot current against voltage or voltage against current, they are going to give us a straight line graph, and we call them ohmic devices or linear devices. Examples are copper, and you should know that what we are currently using to carry power from one electricity pole to the other and to our homes are copper wires. They are copper wires. Then magnesium, tungsten. We used to have a tungsten filament bulb. I don't know if you still have them, but these days we are moving to LEDs and fluorescent tubes so that at least we save energy. So these ones are ohmic devices. They obey Ohm's law. When you plot graphs of voltage against current or vice versa, you're going to get a linear graph. The other ones which do not obey Ohm's law, they don't have a linear current voltage characteristics. We call them non-ohmic devices or non-linear devices. They do not obey Ohm's law. These are devices that do not obey Ohm's law. They have a non-linear current voltage characteristic. That means if you should try to draw a graph of voltage against current or vice versa for these devices, they will not give you a straight line graph. They will give you a curve. And we can look at examples. Filament lamp. A filament lamp, discharge tube, junction diode, a thermistor, a thermonic diode. In one of the past questions, these were jumbled up. Their graphs were put there, and students were asked to identify the graphs to know whether this is a graph of a filament lamp or a junction diode or a thermistor. So if I'm preparing for the exams, I have to look at the graphs of these devices. They are non-ohmic devices. The graphs will not be straight line graphs, they will be curved. Okay. Now, we'll look at Ohm's law and internal resistance, another important aspect of our revision show. Ohm's law and internal resistance. Now, we are saying that in the absence of an external resistor, a voltmeter connected across the terminals of a cell measures the EMF of the cell. I have told you that if you are asked to find EMF of a cell, what do? Just take the cell, connect it straight to the voltmeter, and read. That reading gives you the EMF. That is when the cell is not delivering current to any external component. So this can give us another definition of EMF. It could be the potential difference of a cell in an open circuit. The circuit is open here means that current is not being delivered to any external component. And so in that case, we are saying that whatever you read from the voltmeter across the ends of the cell or the battery is what we call the EMF. This will be the highest of the values you read from the voltmeter, because at this point the cell or the battery is not giving out current to any other load or external component. So we can go ahead and say the EMF of the cell can be defined as the potential difference across the terminals of a cell when the cell is on open circuit. Very important. The cell is on open circuit. The EMF is the PD across the terminals of that cell when it is on open circuit. So I could just get the cell. Positive, negative. Then let me just show an internal resistance like that. Then I'm just connecting the ends of this cell to a voltmeter like that. Here, voltmeter reading is equal to EMF, which I'll use E to represent. Very simple. So this voltmeter here is reading the EMF of the cell. Okay, now, if an external resistor is now connected across the cell, so in the first case, we only have the cell with its own internal resistance. Then we connect it to a voltmeter. It reads EMF, the highest value you can get from the voltmeter. Now, we connect an external device, which is a resistor, across the cell. The voltmeter reading now is called potential difference, PD, across the external. Now, check it. Let's say I have positive, negative. I still have an internal resistance, like that. It used to be like this. The voltmeter there. Now I put in an external resistor. So this is my resistor. So the voltmeter is trying to read the PD across the resistor. This time I'm saying that voltmeter reading is equal to the PD, potential difference. PD. Other books will call it terminal PD. terminal PD. I'll use V for it. And this terminal PD will be less than the EMF because work will be done to overcome even the resistance of this resistor to be able to push the current through it. So because the terminal PD will be less than the EMF, it tells you that some of the volts have been lost. And that difference is what we call the lost volts. So the voltmeter reading V in the second case where you have an external resistor connected in the circuit is less than the EMF on open circuit. The difference is called lost volts. So lost volts is the difference between the EMF of a cell on open circuit and the terminal PD of the cell when it is delivering current. Very important definition. So you would always find out that after you have used your cell or batteries for some time, you find the EMF again, it has reduced. Work has been done. It has overcome some opposition. So we've lost some volts. Good. How do I get the lost volts in a circuit? You have to multiply the current by the internal resistance. So lost volt is expressed mathematically as current times internal resistance. Okay. So we are saying lost volts is the difference between the EMF of a cell on open circuit and the terminal PD of the cell delivering current. Lost volts is the difference between the EMF of a cell on open circuit and the terminal PD V of a cell delivering current. That's lost volts. Now, I want to consider this diagram. Let's say I have a cell. The resistance, the internal resistance. I connect it probably to a key. The key is open. I have an external resistor R. That's the circuit that we have. Now, if I want to apply Ohm's law to this diagram, then I should say V is equal to IR. But in this particular one, the cell is on open circuit, or the circuit is open. So what I have coming from the cell is not voltage, it's EMF. So instead of V equals IR, I'll say E is equal to I. Now watch it. We have two resistances in the circuit. So the two of them must be there. So I have big R plus small r, like this. I should expand, I'll get E is equal to IR plus IR. Now, don't forget I said lost volts is current times the internal resistance. So this value, or this expression here, this is our lost volt. And note that from Ohm's law, V is equal to IR. So this is V. In that case, this expression can become E is equal to V plus IR. If I make IR the subject, I'm going to get IR is equal to E minus V. So you see, when we said that the difference between the EMF and the terminal PD of the cell delivering current is lost volt, we were right. So you can say that IR is equal to E minus V. IR is equal to E minus V. And this is a very important relationship that can help us to solve a number of questions. Good. So let us try our hands on the question. I'm going to try these questions with us. 1, 2 of them Then I expect my students to also call in and try their hands on some other questions. Now, in this diagram here, we want to find the total resistance. So find the total resistance in the diagram here. In this diagram, I have 1, 2, 3, 4 resistors. 3 of them are in parallel connection. This one is connected to these 3 in parallel. So when you have questions like this nature, what you do is you try and find the total resistance in parallel first. So I'm going to find total resistance in parallel. Let me call it RP. I still want to divide the page so I could do everything here. So RP. How do we do it? There are 2 ways. I'll do the first way and I'm doing the second way. The first way is, it says 1 over the total resistance. So 1 over total resistance in parallel is equal to 1 over the individual resistances plus 1 over 5 plus 1 over 2. Oh. Okay? So 1 over 2. So with your calculator, help me, let's do that quickly. 1 over 4 plus 1 over 5 plus 1 over 2 give me 19 over 20. So 1 over RP to give us 19 over 20. But we want RP. So we will say RP will be equal to what? Oh. Fine, we're good to go. So RP will give me 20 over 19 ohms. I'm not through with it, so I'll not change it into, let's say, decimal places, so I'll lose some decimal numbers. No, I'll just keep it like this. Then now, this whole circuit here reduces to this. Two ohms, and the total in parallel, which is RP. So now, the 2 ohms resistor is in series with the total resistance in parallel. So how do I find total resistance? So now, total resistance, which is, I'll make it RT, is just an addition. So RT will give me 2 plus 20 on 19. 2 plus 20 on 19. And with our calculator, we're going to get RT to be 3.053 ohms. That is how you find the total resistance when you have questions like this. There's another way, which I think is faster and it makes working easier, but you have to choose the way that you think it's okay for you. We will still go by finding the total resistance of the resistors in parallel first, fine, and then we will get them in series and we'll add. But in this case, for total resistance in parallel, which is our RP, because I got the product over the sum of products. So I have RP giving me, I'm going to multiply all the resistances. So 4 times 5 times 2. Then all over sum of those products. So 4 times 5 plus 4 times 2 plus 5 times 2. So you see that I've multiplied the resistances from my numerator over sum of the products. So I pick them, pair them, multiply, and add. Multiply, then add. So this is going to give me RP equal to 4 times 5, 20 times 2. That will be 40 all over 5 times 4 will give us 20, plus 4 times 2, 8, plus 5 times 2, 10. So 40 over 38 ohms. I will not bother to go and simplify. That's not my final answer. So then, I'm going to get the circuit reducing to 2 ohms. And the total resistance in parallel, which is my RP. So here, we can now find effective resistance or total resistance, which is maybe RT. And RT, you just add. So 2 plus 40 over 38. And we should get the same answer like we got. 3.053 ohms. This is how to find total resistance when given a circuit diagram like this. You have some of the resistors in series and some in parallel connection. When they are in series, we only add them. But when they are parallel connection, we find the total resistance in parallel. And then the circuit reduces to one of resistors in series. And then we go ahead and we add. Example 2. Since a cell of EMF 6V and internal resistance 0.5 ohm is connected across a resistor of resistance 2.5 ohms. It says, what is the current flowing through the circuit? So, this is Ohm's law internal resistance question. So, let's try and look at our solution. Put down your data. This EMF E is 6V. Internal resistance, I'll say small r, is 0.5 ohm. And then you have an external resistor, which is R, to be 2.5 ohm. Then you're asked to find current. So current to be I, C-U-R-R-E-N-T, I. So we go ahead. What's our formula? It says that E equal to I into R plus R. So we want to find I, right? So I should simply be equal to E over R plus R. What's our E? Our E, 6. So 6 over, what's our small r? 0.5. 0.5 plus, what's our big R is 2.5. That will give us 6 over 3. So the current I will be 2 ampere. That's quite simple. So then, I have a question for my viewers, for my students. This is the part C of the problem of the day. So if you have been following, this is your time for you to also get an award or a prize. You can get a prize for solving this. A battery of EMF 12 volts and internal resistance 1.5 ohm is connected or is required to give a current of 0.5 ampere when connected to an external load of resistance R. What is the value of R? That is our problem to tackle. The phone lines are activated 03022111705 or 03022111706. Kindly call in, help me to solve this question. I will be very proud to hear from you. So that is our problem of the day. Try your hands on it. Give me a call and let's find the answer. And if you get the right answer, we are going to give you something that you will be happy about. All right, I have a call on the line. Hello, good evening.
Hello.
Good evening. May I know your name, please?
Please, Kendra. I'm Kendra.
Okay, Kendra from New Legon.
Please, yes.
Okay, Kendra, do you want to solve the question?
Yes, please.
Good. Let's go ahead. I'm listening.
Okay, so we have E to be 12V.
Okay, 12V.
Yes. And our internal resistance is 1.5 ohm.
Okay, good.
Our current is 0.5 ampere.
Okay, good.
And we're looking for our resistance.
R, good.
Yes, R. So our formula E will be equal to IR plus IR.
So is it by I big R or I small? Which?
E equals I small r plus I big R.
Okay.
And we know E to be 12.
Okay.
IR to be 0.5.
Okay, the I is 0.5, okay.
Yes. And 2 plus R, our big R, the one we are looking for, our resistance we are looking for.
Okay.
So, V will be equal to E minus IR.
Okay.
And then 12 minus 0.5 times 2 will give us 11 volts.
I'm trying to follow you. You go ahead.
Please, after quoting, okay. So that's 12. That's our E.
Okay.
And small I small r 0.5.
Okay.
Times 2. That's a 1.5 ohm. Our internal resistance. So let's say 2.
Why 2?
The 1.5. The internal resistance. So let's say it's 2.
Okay, I don't understand why I say that is 2. I was thinking you would put in the values and we try and find what is missing.
Okay. 12 equals 0.5 times 2, 1.5 plus R.
Okay, so in that case, you want to do E equals I into bracket big R plus small r.
Please, yes.
Okay, fine. Go ahead, please.
Okay, so the 12 equals 0.5 times 1.5 plus R.
Okay, so 0.5 into 1.5 plus R. Okay, go ahead. I'm listening.
So our resistance will be 22 ohms.
Come again.
Our resistance will be 22 ohms.
22 ohms.
Yeah, so you make V the subject, and V will be equal to E minus I small r.
Okay, you go ahead.
Which will give us 12 minus 0.5 times 1.2, which will give us 11 V.
Okay. So what is your final answer for R?
R is 11 V.
11
V.
We want R in ohms.
11 ohm.
11 ohms. Okay.
Yes.
Okay, fine. So Kendra is saying R will be 11 ohms. Fine. That's a good try. When you hang up, try to put 11 ohms into the formula and check whether your right hand side will give you the same answer as the left hand side. And let's see.
Okay.
Thank you for calling. I appreciate your call. Right.
Okay.
Yeah. So we have Kendra on the line. She's been able to try to put down the parameters. That's okay. She gave us the formula she thinks we should use. E equals I into big R plus small r. That's also okay. I was thinking she would just go ahead and just put in the value so we could find R. But it looks like along the line we lost track of what she was doing. But her final answer, I am afraid, is not what we have here. So I'll still wait for another person to call in and try his or her hands on the question. And I am sure that Kendra, you can come again and see what we can do.
Good evening, sir. My name is Joseph.
Okay, Joseph, good evening. You are welcome.
Thank you, sir.
Yeah, someone tried to give us the solution, but along the line we lost track. We have the parameters given to us. Can you continue with us?
So we have our EMF to be 12 volts.
Okay.
And we have our R to be 1.5 ohms, and we have I to be 0.5 ampere. So we are having our formula to be electromotive force is equal to I equal to capital R, capital R plus small r.
All right.
Then we have I'm trying to make big R the subject.
You want to make big R the subject?
Yes.
Okay, let's try and see.
So when you make big R the subject, you get R to be equal to the electromotive force over the current minus R, which is E over I minus R.
Minus small r.
Yeah.
Okay.
So we have the capital R to be equal to, when you put in the parameters, you get 12 over 0.5.
Okay.
12 over 0.5 minus 1.5.
Okay.
So that will give you 22.5 ohms.
22.5
ohms.
Excellent. That is the answer.
Thank you very much.
Well done, Joseph. Well done. Thank you for calling. I really appreciate your being with us on the show this evening. In fact, Joseph has done justice to the question. So I'm sure, Indra, you've seen where you put it a little bit along the line. So he tried to make out the subject from the relation there. So from here, made out a subject, put in the values, and you have that. Well, you don't always need to go by this way by making out a subject. Right from E is equal to I into R plus R. We could still put in our values. We have E to be 12, we have I to be 0.5, and R we don't know, but small r to be 1.5. We can still work it out and say 12 is equal to, then you have 0.5 multiplying everything in the bracket. So 0.5 r plus 0.5 will multiply 1.5. That'll give us 0.75. Then we group like terms. So you're going to get 12 minus 0.75, giving you 0.5 r. And that on left hand side will give us 11.25, which will give you 0.5 r. So r will just be 11.25 over 0.5. And the answer should be the same as 22.5 ohms, just like Joseph got for us. So if making out the subject, pick out the subject is a problem or will be a problem for you, all you can do is to just put down the formula, put in the values, try to expand, make out the subject along the line, and you'll be good to go. So thank you, Joseph. That's a good one there. That's really, really refreshing. Good, good. So we can now move ahead and look at another thing. Factors that affect the resistance of a conductor. Because we have a question on resistivity. So when you know these factors, it will help us to come up with what we term resistivity of a conductor. So one, impurities. So impurities will increase the resistance of a conductor. Length of the conductor. The longer the conductor, the higher the resistance. The electron theory tells you that resistance comes about when you have atoms knocking off a stream of electrons moving in one direction. And according to the theory, a stream of electrons moving in one direction will make current get produced in the other direction. So if you have some of these electrons being knocked off the line in which they are moving, then you have few of them moving in a straight or particular direction, the amount of current that will be produced will be less. So if you have a very long conductor, it means the number of atoms that would be encountered by the electrons will also increase. Therefore, it will affect the resistance. So the longer the conductor, the higher the resistance. Then temperature. As temperature increases, it can affect, it will reduce, or it will make the amount of current that will go through the conductor reduce. That means that the resistance is going to increase. That's for a conductor. It will not be so for a semiconductor anyway. Now, for cross-sectional area, that one, a conductor with a higher or a bigger cross-sectional area has a low resistance. So if you want to decrease the resistance of your conductor, it's better you go in for one with a bigger or a larger cross-sectional area. So these are the factors that will affect the resistance of a conductor. Good. So from the factors that affect the resistance of a conductor, we can look at resistivity. Okay, we have said that the resistance of a conductor is directly proportional to 1, the length. So resistance is proportional to the length, L. Then the same resistance is inversely proportional to the cross-sectional area. So we can say R and area, or cross-sectional area, are inversely proportional. If I put these two together like this, I'm going to get R proportional to L and inversely proportional to A. So I have R, that L on A. If I do away with the sign of proportionality, I bring an equal to sign, and I'll introduce a constant. So I have R is equal to, that's my constant, L on A. Now this constant rho is called resistivity. Resistivity. So if I make that the subject, I'm going to get resistivity is equal to RA on L. Resistivity is equal to RA on L. So how do I define resistivity? I'll say resistivity is the ratio of the product of the resistance and cross-sectional area of a material to the length of the material. I wish I could parrot on and take you all the way to get the other expression for resistivity, but time is not our friend at this moment. Time is not on our side, but I believe you have enjoyed the revision. We will come your way with more revision shows as the weeks go by. So make a date with us on this channel, the Joy Learning Television channel, on Facebook and on YouTube. And Pabi Albert is my name. You can call me Pius. It's been a delight having you, all those who called in, Mabel, Joseph, Kindra, Daniel, Salamatu. I appreciate your time spent with us. So keep working harder, keep doing all you have to do to pass, and be consistent. So till I come your way another time on the Joy Learning TV revision show, I want to say it's bye-bye for now. Have a very good night. Thank you for being with us.